everybody, welcome to day two. So we're going to do a PowerPoint here today through this video, and then I'm also going to link this PowerPoint to our Google Classroom, so you will have access to the video and the actual PowerPoint to go through at your own pace. Today we're going to cover two sections in our book. The first one is going to be section 1.8, Statements of Logic, and it kind of ties in closely with section 1.7. So those are the two sections that we're going to cover. In section 1.8, we're really focusing on recognizing what conditional statements are and what are they. We typically see them in if-then form. So a conditional statement is just simply saying, if this happens, then this will be the result. We're going to focus a lot on this. This is what a lot of geometry covers, is if this, then that. So if you see here, if you dig deep enough, then you will end up in China. If you break a mirror, then you'll have 7 years of bad luck. If you step on a crack, you'll break your mother's back. So these are all conditional statements. It's upon a condition of something occurring or happening, then there will be a result. In geometry, we use shorthand a lot. We use P and Q. P is going to represent your hypothesis, and Q is going to represent your conclusion. And then we can even shorten it up even more and go with P arrow Q, as implying P implies Q. The hypothesis implies your conclusion. So that's kind of our brief overview of what a conditional statement is and looks like. Now, these statements all have alternatives, so we can negate certain statements on here. So when we negate something, it's just basically adding the word not in front of it. If this does not happen, that's a negation. And the word not is represented by this little tilde in front of your variable, in front of your letter, representing your hypothesis. So if I say math is cool, the negation is that math is not cool. And we all know that's not true. So negation doesn't always mean truth. We're going to talk a little bit about truth and truth in these statements as well. Math is not cool. Well, if you negate that, you get a double negative. Math is not cool. So you don't put two nots in there and you go with just math is cool, and then we're all really happy. So if the not is already part of your conditional, to negate it, you just get rid of the not. And that brings up the following statements that are associated with conditionals. You have the converse, the inverse, and the contrapositive. And a lot of this is going to stem from the negation of certain parts of our statements. And it's also going to stem from the order in which we make our statements. So remember, a conditional statement says, if P, then Q. The converse of that, we switch our hypothesis and conclusion. And we'll go through a few examples of this in a minute. So the converse of a conditional is when you take the original conclusion and state it as your hypothesis. The original hypothesis is stated as your conclusion. The inverse is when you keep the order the same but negate both statements. And then the contrapositive is a combination. You switch the order and negate both statements. Biconditional statements are stated as Q if and only if P. We'll talk more about that in a minute. So, find the converse, inverse, and contrapositive of these statements. If an animal is a fish, then it can swim. Okay? Converse, really cool swimming animal. Converse is when we switch our conditional and our hypothesis and our conclusion. So the converse, we're going to say that if an animal can swim, then it is a fish. We aren't going to say if it can swim, then an animal is a fish. So you always have to state, that's just more English language than geometry or logic. Inverse is when you negate. So if an animal is not a fish, then it cannot swim. Contrapositive, you do both. If an animal cannot swim, then it is not a fish. Some statements are not necessarily true, just because the original statement is true. Okay, so if the statement is true, all of these other additional statements might not be, and we're going to do some investigation and truth into that in a few minutes. starting with theorem 3 here. If a conditional statement is true, then the contrapositive of the statement is always true. If P, then Q. If not Q, then not P. If one is true, the other is always true. Assume that the conditional statement is true. You speed, then you'll be given a ticket. Julia's not given a ticket. Okay? So we've been given an information of not Q. Can we draw a conclusion? Well, I can conclude that if P, so if I know P, I can conclude Q. But since the conditional and contrapositive are both true at the same time, if I'm given not Q, I can also conclude not P. The conditional statement had P being speeding and Q, the result, being given a ticket. Julia is not given a ticket. That is not Q, not the original conclusion. I can conclude not P. Julia was not speeding. Okay? For Emma sped, I can conclude, well, she's going to get a ticket, or she got a ticket. Okay? These are going to lead us into the chain of reasoning, or what we call the law of syllogism, or just the chain rule. I am told that if a given statement is true, I can draw a conclusion. If I know that conclusion is true, I might get another conclusion, which means I can skip that middle ground altogether. I can chain these together. We'll see that here in a minute. Okay? If people live in Vernon Hills, then they live in Illinois. P then Q. If people live in Illinois, then they live in the United States. Well, we already said that living in Illinois was our conclusion, Q. Well, living in the U.S. we haven't used yet, so we use a different letter to represent that. This is now saying Q then R. That allows us to conclude that if people live in Vernon Hills, P, that goes to Q, Q goes to R, they live in the United States. We can conclude that P goes straight to R. Okay? Does not matter how many things we can chain together. We can make that chain 10 different statements long as it continues in that pattern and chains through, you're following a law of logic. Okay? So if you give a mouse a cookie, we're not going to read this right now over this video, we don't have time, but if you've read that book before, that's a big if-then chain of reasoning logic statement. Okay? All right, now section 1.7, deductive structure. And yes, this did say we'll look at your project. I'm going to play this video separately, and I'll include a separate link in our Google Classroom so you guys can watch that. All right, deductive structure. The goal is to be able to understand the structure of geometry and understand the characteristics of theorems. Deductive structure is the four following elements: undefined terms, postulates, and definitions. And these are three elements, I guess. Something that is not determined by previously developed concepts. So points aren't developed, they're just in lines. They are undefined terms. We kind of described them yesterday, but we didn't define them. Postulates are unproven assumptions, but they are assumed to be true. Geometry is built on tons and tons of postulates. A few undefined terms and a lot of postulates. The rules of algebra, there's no way to formally prove some of those. Definitions are the meaning of a concept, and these are going to be very important and mostly if-then statements. And they are biconditional. They can also, be written in conditional form. Those are our if-then statements. So if we think about what a midpoint is, and we'll get more into this and define this a lot more as we get further along in our class, but a midpoint is that if a point is the midpoint of a segment, then the point divides the segment into two congruent segments. And a lot of vocabulary within that vocab word, but that's a key important statement here, and it's a definition. It's an if-then form. If a point divides a segment into two congruent segments, then the point is the midpoint of the segment. That's the converse. They're both true. That's what makes a statement a biconditional statement. If the conditional and the converse are both true, it is biconditional, which means we can say that the midpoint of a segment, a point is a midpoint if and only if it divides a segment into two congruent segments. And we can reverse that. Theorems is our fourth one, and theorems are mathematical statements that can, and we often will, be proven. These are the things that we're going to spend a ton of time on in this semester, proving algebraic and geometric theorems using a few different variations and a few different methods. Okay? They are not always reversible. They're not always biconditional. They can be. Okay? If two angles are right angles, they're congruent. Done. Easy. Okay? But if two angles are congruent, they are right angled. That's the converse, but it's not true. I can come up with a lot of different angles that are congruent, same measure, but are not right angles. It could both be 40-degree angles, 38-degree angles, whatever. So by giving those examples, those are called counterexamples. And a counterexample just proves that this is not a definition. That makes it a theorem. Okay? So this is not a reversible statement, which makes it a theorem, not a definition. Okay? Now, next thing I want you guys to do is I'm going to post on our classroom that video that was here. Let me try to scoot back to it. And I'm also going to post a copy of a project that I'm going to want you guys to be working on, and we'll talk a little bit more when we get back together on when it is going to be due. But you're going to have at least about a week to get that done. So take a look at the notes, take a look at anything else that you guys need, take a look at this again if you need to, and we will hopefully be back in really quick.